When we talk about sampling distributions, you might come across a term called the central limit theorem. All this refers to is if we take enough samples and large enough sample sizes from a parent population, our sampling distribution of means will be approximately normal, regardless of the shape of the parent population. We have a script here in R to illustrate this process. If you want to follow along, you can download it from the following link below and just click on the run to step through each of the lines of code. This works most well with RStudio. So we're going to go through here and through these first few commented lines. And first we're going to draw 500 random numbers from a normal distribution using this rnorm command, initialized with a mean of 100 and a standard deviation of 10. So we've done that, and now we have a variable called x. It's numeric, and it has 500 elements. If you want to see each element's value, you can uncomment the following line and just return the value of x. Next, we're going to plot a histogram of these random values we've drawn from the normal distribution using the hist command. Okay. Next, we draw another set of 500 random numbers to compare it to the histogram that we just created. So, identical command as before, the numbers will be slightly different because, again, we're sampling random numbers from a distribution. And again, we plot those, and it's roughly similar in shape to the previous plot. If we want to see how this overlays with the normal distribution, we can use the curve command to superimpose a red normal distribution line around our histogram. And you can see it approximately follows the shape of the normal distribution. You can get more information about the commands and arguments going into the curve command in the text of the file. So now that we've done that, now we're interested in creating a sampling distribution. In other words, for each of these samples that we create, we're going to take the mean of those and then plot the value of each of those means. So to do that, first let's look at the mean of our 500 randomly sampled numbers from the normal distribution. Recall that we had a normal distribution with a mean of 100, and the mean of all those numbers is very, very close to 100. Not surprising because we selected a large sample size of 500. Okay, so if we do this again, sample 500 random values and plot the mean, you can see that again it's very, very close to 100. These means are not very different from each other. To build the sampling distribution, we're simply going to sample several samples of size, let's see here, n, which we can initialize to be 5. And after we calculate each mean of a sample size of 5, we plot that mean into a new histogram and then chart the histogram. So first of all, we create an empty vector, and we're going to call this variable x bar. Next, we can populate this value by using a for loop. So for each element, 1 to 500, randomly sample a sample of size n from a normal distribution with a mean of 100 and a standard deviation of 10. Once we've done that, you see we have a new variable called x bar with 500 values. And if you want, you can look at all those values to see the mean of all of these samples. And you can see here that they're much more tightly clustered around the true population mean of 100 than we would if we randomly sampled, say, 500 values from a normal distribution. We're going to go ahead and plot those in a histogram, and you can see that the spread of this sampling distribution is much more narrow and tighter around the population mean of 100. You take the mean of this, and you can see that the mean of the means is even more close to 100 than it was from any one of the samples. Next, we're going to see what effect increasing the sample size has on the sampling distribution. By increasing the sample size from 5 to 10, we hypothesize that the sampling distribution spread is going to be much more narrow and much more tightly clustered around the mean of the population. So again, create another x bar variable, create another for loop to populate this variable. Okay. So another histogram, you can see it's even more tightly centered around 100. Lastly, we have a summary of the central limit theorem, which states that if you draw samples from a normal population, the sample population will be normal also. The mean of the distribution of sample means is identical to the population that the samples are drawn from. And lastly, the higher the sample size that is drawn, the less spread there will be in the sampling distribution of the mean. In the next tutorial about the central limit theorem, we're going to show how, no matter what the shape or the skew of the parent population, the central limit theorem for the sampling distribution of means still holds.